the right-hand side, there are 4 normal distributions which can map into to map to 4 points on the left, which is the 4 points in the upper half, right? Now, if you think about this method more carefully, what about the boundaries of this set? Okay, namely, normal distribution. When sigma go to say 0, okay, we have this delta function, right? When sigma go to 0, so when sigma go to 0, it's the real axis here. So the real axis with a particular location on the real axis index a delta function, a generalized distribution. Okay, so this worked out well. What about the other end? Okay, when sigma goes to infinity, right? Sigma goes to infinity. So when sigma goes to infinity, the normal distribution becomes more or less a uniform distribution. Okay, but still there is a location kind of parameter that's indexed. So in that way, you can think about this as being now the upper half plane can be extended into the infinity. But of course, it's not the one-point completion because you have many different points, right? So in that way, at least we can map the whole set of normal distributions into this well-defined geometrical object of our plane. Having done that, the next question that we want to ask is that what kind of a geometry can we prescribe to the upper half plane that reflects our statistical intuition? So our statistical intuition tells us that if you look at these 2 normal distributions by the blue lines, these 2 distributions are more distinguishable than the other 2 distributions that's indicated by the red line, because they have a smaller standard deviation, right? So they are more distinguishable, they're more different. So we want the geometry on the upper half plane to reflect that, to reflect the fact that, say, these 2 lines, these 2 dots correspond to the red. The red line is closer together, because they are more, they are less distinguishable distributions compared with the 2 blue dots. Okay, so that is to say we have to put some like non-trivial, non-Euclidean geometry on the upper half plane. We can't just simply put the Euclidean geometry for that, right? So based on statistical consideration, that's something we want our geometry to have. So in fact, turns out that if we put this sort of Fisher-Rao metric, which we'll talk about this later on, turns out this normal distribution would have the metric would have a constant negative curvature. Okay, so when we choose the right kind of a metric, turns out the normal distribution, the upper half plane, it is a plane endowed with a constant negative curvature, which is the simplest model, the Poincare half plane, or raw model of the half plane, and that's the simplest kind of a geometry. So we see a nice correspondence between a statistical object on one hand and a geometric object on the other. And this fact actually was incidentally discovered by Amari in the 1960s, which motivates him, as he said, to study, to investigate this kind of a relation between statistics and geometry. So it turns out that for this normal distribution, the new sigma coordinates, okay, which is what we parameterize that distribution, is not the best kind of a coordinates for that. It's statistically meaningful, but on the other hand, geometrically speaking, you can introduce 2 new sets of coordinates, x and u, as transformations of this mu sigma coordinate. Okay, under this x and under this u coordinates, turns out that this Fisher-Rao metric have very simple expressions. The expression being the second derivative of some potential function. Okay, so the potential functions are written as follows. So x, so there is a potential function that's associated with x, and there is also a potential function that's associated with u. And furthermore, these x and u are in what is known as Legendre dual. So the normal distribution turns out to belong to a family, what is known as the so-called the exponential family, which enjoys a very nice duality, and it's reviewed by the fact that there is a pair of conjugate potential functions, each corresponding to or each inducing a coordinate. It turns out that if you think about like the u coordinates, okay, the meaning of the u coordinates here is kind of a straightforward. In a sense, it's really the first moment and the second moments. Okay, so the moment coordinates. Okay, so that fact is very important as we move on to discuss about statistical inference and what information geometry captures for us. Now, a quick kind of a survey of information geometry in terms of, so information geometry by definition, so narrowly speaking, we're talking about, this is a differential geometric study of the manifold of parametric probability distributions, with a given support. So we always start with a given support. We look at all probability distributions on that support, okay, and the class of the family of all the distributions, and in particular the parametric ones. We can use the parameters as natural charts on this geometry, on this manifold. So Rao identified the Fisher information as being a metric tensor on this geometry, and it was not until like 1975, that Brett Efron trying to give meanings to the curvature of this geometry. So give some statistical interpretation of the curvature. But then David realized that in fact you can put multiple versions of so-called affine connection on this manifold. And curvature is really associated with affine connection. So David initiated some study of sort of flat connection on this manifold. And Amari systematically studied this notion, the idea of putting a family of connections on this statistical manifold, and systematically advanced this theory. And Eguchi provided a way to link the so-called divergence function, so any statistical or divergence function, contrast function, to this geometry. And then in 1987, Stephen Lauritsen was able to define statistical structure very abstractly as a geometric structure. So at that point, statistical manifold is a well-defined geometric concept that can be independent of its statistical realization or model. So let us see where does this geometry arise in the very abstract setting. So I suppose there is a good group of statisticians in the audience, so I will start with a statistical introduction. Information geometry can be introduced with some other motivation as well, but from a statistical perspective. So we start with a measure space, okay? Measure space, omega is our sample, mu is our reference measure, okay? So if you look at any model, okay, any probability model on this, okay? Upon observe some data, omega, small omega, upon sampling, that is to say, there's a loss that incurred with any model, and this loss would satisfy this Jackson inequality. So here, Q is any model, and P is the true distribution that generates the data. It's the underlying true distribution that generates the data, the generating process. So the Jensen inequality gives that the expected loss is minimal, okay, when your model of the world is what it reflects the true nature of the data generating process. So that just reflects by this very well-known first being the Jensen inequality, or data processing inequality as known in grading theory. Now, once you have that, if we take the difference between the expected loss of the model, so E expectation, the subscript P is with respect to the P, which is the true data generating distribution. So when we take the expectation of the loss of the model Q, and the difference of that with respect to the minimum loss, this is nothing but the KL divergence, which is very well known in statistical machine learning. Okay? So the KL divergence is nothing but just the difference between the expected loss and the minimum loss. Now, of course, there can be different kind of loss functions that we can introduce. The most general ones for describing probability density functions are the so-called F loss, okay, the F function introduced by César. César replaces this minus log with arbitrary convex function which satisfies some conditions about the derivatives values in one. And then you have this F loss function, it's most general homogeneous loss function. Okay? So now, if we're dealing with parametric models now, so here I use X to represent when we speak of the parameters. The X is a vector of a parameter. So the parameters indexing the model distribution P and parameter indexing the model distribution of Q. Okay? So if we now have parametric models, then these divergence functions, essentially, they are basically functions, the two-point functions, right? Two-point functions on these parameters. So we have XP and XQ. F divergence, we also have XP. So that's so straightforward. Now, the first thing to appreciate really is that for all this divergence function, so now let's denote L as the log of P. Okay, L is the log of P. So P is the x is the parameter, omega is the sample space value. Okay, so now let's do Taylor expansion of this divergence function. Taylor expansion. Taylor expansion in the neighborhood of xq is near xp. Okay, the zeroth order disappears because that's the definition. The first order tends to also disappear because of smoothness of this log function. It's a second order that's first survived, and then the survived term is, we can identify it, so we call it as g. So here we have the log p, and the partial xi stands for partial xi. So partial xi, and this partial xj is partial j. So take partial derivative with respect to xi, and then partial derivative with respect to xj, right? So we get this gij as a function of the parameter x. So this quantity is semi-positive definite, as you can show readily because of this. Okay, so this is actually turns out to be this is in fact what's being identified as the Fisher-Rao metric. It's a Fisher-Rao. So you do Taylor expansion of the divergence function. When you get to the second order, it's Fisher-Rao. Now let's keep expanding to the third order expansion. Third order expansion is also a very important quantity now. People realize. Now it gets a name called Amari chains of tensors. Essentially, it's a triple correlation, right? So you have the x. So this is a score function, okay? Partial log p, partial xi, partial xj, partial xk. So you have the ijk, okay? You have the triple correlation function, the cubic form. Now, what's interesting? So okay, you think okay, let's expand KL divergence. You get these things. No, so what's the big deal? The big deal of that is that when you expand F divergence, okay, the F, you remember F is an arbitrary complex function, right? You get identical Fisher information. By identical, I mean it differs by a constant. Okay? And you get identical third order expansion. Okay, so you get identical things. Okay? They only differ by a constant. Okay? So this is actually quite remarkable because that means, regardless of what kind of divergence function you choose, the resulting second order, third order kind of quantities are the same. So that indicates that these are somehow some invariants of statistical models. And in fact, it can be argued very rigorously, and these are indeed invariants. And these are the second and third order invariants of a statistical model under what is called the Markov morphism of the sample space. A Markov morphism of sample space is that if now I relabel the random variables, right? I have another new random variable, so my statistical model should respect this kind of relabeling, okay, and in statistical distribution of an old sample space and new sample space, they should transform in some way, okay, that respect this relabeling. And if you want to ask then what is left as being invariance of this model, and the second order would be this one, and third order would be that. So these are the only actually second and third order invariants of the Markov morphism. That's shown by Chenzov first, and then it's being also shown or extended, generalized by other authors as well. So now, with this second and third order invariance of statistical model, we can construct a geometry. We can construct the following geometry. From the second order quantity, right? The second order, we can identify this as a Riemannian metric. We can use, because it's semi-positive definite. So we identify this as a Riemannian metric. With a Riemannian metric, it always comes up with what is called a Levi-Civita connection. This is a third order quantity which can be uniquely specified by the Riemannian metric. I'll talk about this a little later. Now, what we do is that we use this Riemannian metric, the second order quantity, and then we construct a family of these, like the third order quantities, which is the Fn connection. Okay, so here, this is called this user gamma. So in Amari's book, you will read about this. This gamma, the alpha is a parameter, is a real value. Okay, the first term is the Levi-Civita connection. This is a connection which is constructed by metric, by the G. It's well defined by taking partial derivatives of the G. Okay, you can calculate that. And then the second term is using the T, the third order invariant quantity. And we deform it, we change the Levi-Civita connection by this alpha, by this alpha value, alpha can range from this. So when alpha equals 0, it's just a Levi-Civita connection. So any alpha is just general. Now, if we want to explicitly write this out, we have this expression. Okay, you can find it in Amari's book, so forth. So L is the log of P, and this is partial xi, partial xj, and here is partial xi, partial xj, and then this is partial xk on this. So now, this family of connections, when alpha equals 0, is a Levi-Civita connection. But turns out that alpha equals +1 and minus 1 are the two very important affine connections. One is so-called the E connection, one is called M connection. Because these connections are the good connections or the most appropriate to use for dealing with the exponential family or mixture family. So these are but these two connections turns out to be in a kind of a dualistic, arranged in a dualistic way. So there's a conjugacy relation. In general, alpha connection and the minus alpha connection are in this dualistic relation. This star indicates a dualistic relationship, which is well defined. I'm going to introduce later on. So 0 is due to itself, which is the Levi-Civita, and then alpha is a mixture of the one connection and minus one connection. So I think at this point, let's just review intuitive meanings for these geometrical quantities for these equations. So on the differentiable manifold, okay, so we can prescribe the following structures very independently. Okay, so the first we can prescribe a metric structure. Okay, the metric structure. A metric structure basically allows you to measure the geodesic of 2 points, the shortest distance of the 2 points, right? So, and it also allows you to define orthogonality of two vectors on its tangent space, okay? Orthogonality. And then for the metric itself, you can talk about the conformal equivalence of different metric. Conformal basically they are isotropically expanding the manifold. Now, so that's one structure. You can prescribe it. Independent of the metric structure, even without the metric, we can prescribe a so-called connection structure. A connection structure, what it allows you to do is to compare tangent space at one point and neighboring points. So it allows you to compare vectors in tangent space with vectors in neighboring points of the tangent space. So therefore, it defines what is called a parallel transport. So you have a vector at one point. How would you parallelly move it to a vector in neighboring points? Okay, so it's parallel transport. So this connection structure would define what is called autoparallel curves. Autoparallel curves are the curves whose tangent vectors are parallel to each other. So you can imagine a curve. At each point, I have a tangent vector, and if I move this tangent vector in a parallel way, that becomes a curve. That curve is called an autoparallel curve. Now, if you may recall, when you read a lot of textbook in Riemannian geometry, you learn about these two concepts. But these two concepts are interchangeable. In other words, your general knowledge about this Riemannian manifold is that if you have any 2 points, there is a unique geodesic that connects the 2 points, right? So the shortest distance, but this shortest distance curve is the distance minimizing curve is also the autoparallel curve. That is to say, the tangent vector is parallel to itself. Okay? But actually, rigorously speaking, the more accurate statement is as follows. For any Riemannian metric, there is an associated affine connection. This affine connection, it's a connection that defines the parallelism. Metric only defines the length, talk about distance minimizing. So for the Riemannian metric, the connection, which is called the Levi-Civita connection, and the metric is such that they are compatible. In other words, this autoparallelism and distance minimizing, these two concepts are more or less are the same. But you need a very special kind of connection to do that. And this connection is called the Levi-Civita connection. And this Levi-Civita connection is the one you will read about in most of the textbooks, including in the physics application. Now, but the important thing to know is that on the manifold you can put different connections. You can put a connection independent of the metric. You can put a connection unrelated to the metric, or you can impose different kind of compatibility conditions of the connection with the metric. And this is precisely what information geometry does. Information geometry extends this Levi-Civita coupling of the connection with the metric to make it more generalized, to allow a kind of duality. Okay? So another important thing to know is that in terms of the geometry, it is the connection that gives rise to so-called curvature and torsion. So connection on a manifold, you can discuss its properties, namely its curvature and its torsion. Okay? So when you say a manifold is curved, you mean there is a curved on non-zero curvature connection. Okay? But a lot of time we say the metric is curved. Well, this is a simplified version to say that the connection corresponds to the metric is curved. Okay? So it's very important to make the distinction between these two concepts, but these two can be separately conceptually defined. Now, on manifold, the third thing, which is also separately defined, independent of the first two, which is the volume element. Okay? And the volume, we're talking about oriental manifold. Okay? So the volume, it basically gives rise to a measure. So it allows you to do integration of functions on the manifold. And this is going to be important as we should go on to talk about its application. So okay, so now rigorously speaking, now here's something I'm really speaking to geometers here. So let's define the relationship between the connection and the metric that information geometers have used. Okay. So let's say on the differential manifold or orientable differential manifold M. Okay, we already said we can prescribe a metric and we can prescribe a connection. These are two independent concepts. Okay. Now, let's first introduce this concept so-called conjugacy. So, given any connection, there is a well-defined way to transform to create another connection, which is conjugate with respect to G. Conjugate in the sense that there are a pair of connections which are dual to each other, and the second conjugate becomes the original one. And if you use them both, you have to use them a pair to preserve the length that you are. When you do a Riemannian metric, it needs to take in two tangent vectors. So you use one to parallel transport the other to transport the other. In that case, it will preserve the inner product. Okay? So you are using two connections, one to transport its first tangent vector field and the second to transport the second tangent vector field, so that the Riemannian tensor, when it operates on these vector fields, are preserved. So this is called a G conjugate. Well, G conjugate is a generalization of a Levi-Civita conjugate in the sense, the Levi-Civita metric in the sense, Levi-Civita is self-G conjugate. It's conjugate to itself. It's just conjugate to itself. So the first notion is so-called a G conjugate. The second notion is called the nabla and G. We can give a kind of coupling, and this coupling gets its name. It's called Kudazi coupling because it's using affine geometry. Kudazi coupling is to impose this kind of a relationship. Okay, you just write it out. This covariant derivative. So basically, the covariant derivative allows a kind of a twisting, kind of a compatibility relationship. Okay, so this condition is also satisfied. So this condition says that basically the metric need not be parallel with respect to the connection, even though nabla G may not be zero. For a Levi-Civita connection, the metric is parallel to the metric. I mean the connection, Levi-Civita connection and metric, they are parallel to each other. So nabla G is equal to 0, and this way is a more generalized version of. So both of these are generalizations of Levi-Civita, the ideas behind the Levi-Civita connection, the Levi-Civita coupling of the metric connection, but they are generalizing in two slightly different directions. One in the direction of conjugation, duality, conjugation. The other is in the direction of coupling, how metric and G are coupled. Turns out that now these two generalizations themselves are linked by an identity, and it is a very crucial identity. The crucial identity is that, so this is derived, which is on the left-hand side is a lack of coupling, on the right-hand side is a difference of torsion. So essentially, it says that Kudazi coupling of a metric with a connection is equivalent to saying that the torsion of the connection and the torsion of its conjugate connection, they are the same. They are equal. Okay? So Kudazi coupling gives rise to a condition of preserving torsion. So because of that, we can have the following two, which is equivalent ways of defining statistical manifold. This is the manifold of the parametric complex models that Amari uses. So the statistical manifold. So the statistical manifold, there are two ways of describing it. One is saying that, okay, we have a manifold, we're given a metric and given an FN connection. And that the metric and the FN connection is quasi-coupled. It has this kind of a unique kind of coupling relationship. And furthermore, this connection is torsion-free, no torsion. Which is equivalent to another definition of statistical manifold, which says that we have a manifold with a G and with a pair of torsion-free connections. The pair being nabla and nabla star. If they're both torsion-free, and they are compatible, they are dual with respect to G, we call it statistical manifold. So this is the object that we study for statistical manifold. Okay. So I'm going to talk about. So this object arises very naturally by divergence function. So in fact, in a couple of slides down my presentation, you will see that any divergence function can give rise to this structure. So it's a very easily obtainable structure. I'll just quickly mention about the volume. So this was actually based on some work about Subrani in 1997 in a Yale computation paper. He basically showed that how the Riemannian volume form can be, in a very rigorous sense, well, I mean, we know in Jeffreys prime, right? Jeffreys prime, we know the formula for the Jeffreys prime using the Riemannian volume density, okay? But he gave a very rigorous argument as to, from the perspective of distinguishable models at any. So our manifold, each point is one model. So a slightly neighboring point is another model, right? So any volume, a small cube in this manifold, there's just a lot of models there, right? So you can impose that interpretation of the distinguishability of the models. So he did a very thorough analysis and showed that how this distinguishability of different model class and so forth, they can be related to the Riemannian volume form, and this is precisely what Jeffreys prime is. Okay, so Jeffreys prime essentially is a Riemannian volume form, or the Riemannian volume form is one which is parallel with respect to the Levi-Civita connection, Okay, so Amari generalized this idea. To a so-called alpha volume form. To alpha, this is a work by Takeuchi Amari. Amari is able to generalize this idea of the invariant parallel or invariant volume form by looking at the alpha connections. So what are the invariant volume forms under the alpha connections, and using those as the Bayesian prime, because these are Bayesian non-informative prime. After he has done so, he's able to show that the following various statistical estimators, which are commonly used by statisticians, they are related to each other. So ML is the maximum likelihood estimator, and then T is the derivative, the partial derivative of the log of the Riemannian volume form with respect to the parameter. And the three classes of the projected Bayes, the minimum description length MDL estimator and the bias corrected MLE, they are all related to each other by this unifying formula, except for different alpha values. So it shows that by resorting to the non-Levi-Civita connection, in fact it's alpha connection, it has some advantage of potentially unifying the different statistical estimators in this geometry. Okay, look like a So now maximum entropy, minimum divergence inference. I want to use this example to show make a particular case for duality. So we'll know maximum entropy inference, which is if we if we want to get a particular probability density function subject to some knowledge, prior knowledge, we can write this knowledge, prior knowledge as being constrained on this some f sub I, these are known functions, and we maximize the entropy with respect to subject to these constraints. Okay, so this principle is similarly used or described as the minimum divergence principle, because in minimum divergence case, basically you have a reference distribution, and when you use a reference distribution with respect to reference distribution, the two principles are identical. So now, what is the probability distribution that is the solution to the maximum entropy principle? Okay, so maximize the Shannon entropy subject to this constraint. Well, we can perform Lagrange, use the Lagrange multiply methods, convert this constraint optimization problem to an unconstrained optimization problem, and then after you just do this, it turns out that this is the exponential family. So the exponential family in the sense that, so now the xi's are the Lagrange multiplier. The f sub i's are the known functions, are the known random variables, and then the phis or the log z is the partition function which has this form, okay? And the u's are the known constants are related to the Lagrange multiplier by this, in this way. This is the first derivative. So the second derivative of this is nothing but the covariance of this f functions, okay? So this is a quite standard in maximum entropy inverse. Now, through this example, what we learned is that in terms of specifying a probability distribution, right? We can specify. Let's say what is the solution to the maximum entropy principle. This is a way of specifying a particular distribution. We specify that by saying, okay, so maximize the Shannon entropy subject to these constraints. These constraints we have these parameters used, okay? And the solution to that is an exponential family where the xi's can be taken as being the natural parameterization of a family. So you have a duality between x and u, in statistics. This duality in specifying the same identical statistical model. So one probability distribution, you can either use the x, the natural parameter, or in this case is the Lagrange multiplier, which will be specified by u, or the u, the constraint parameters, okay, expectation parameters. So these two are in kind of dual. In fact, this is they follow the Legendre. This is the Legendre relation of this. So the partition function, the moment generating function, the Legendre of that is just the entropy, it's just Shannon entropy. Okay, so there's a nice duality between the two. So this kind of duality leads to the following notion in invariant geometry, namely the so-called bi-orthogonal coordinates. Bi-orthogonal coordinates, to think about now on this manifold where all probability distributions, right? We specify by x as being index each distribution. Now we can take a transformation to a new coordinate u, which is another set of coordinates specifying the same points. That's just change of coordinates to a different kind of coordination. So let's look at this x to u coordinate transfer, and then we can look at this Jacobian for the coordinate transform. Turns out that this Jacobian of the coordinate transform is nothing but the Riemannian metric. So this x coordinate system itself is not orthonormal. It's not orthonormal. So in other words, if you take one xi and xj, the inner product is not delta ij. It's not orthonormal, and neither is u coordinates. But on the other hand, if you take one element from x, another element from u, then if you perform the inner product of these two, that becomes delta ij. So it's orthogonal. So it's bi-orthogonal. So you have two sets of coordinates on the manifold. If you take one from one set and another from another set, then you perform the product of this becomes a delta ij. It's orthogonal. So that's why it's called bi-orthogonal transformation. So this bi-orthogonal transformation, or the bi-orthogonal coordinates, is a very special feature for this geometry, for the so-called Hessian geometry. This is dually flat geometry. Okay, and this actually has some application to machine learning. Right? Supposed to be there are machine learning audience here. So if you think about like standard online gradient methods, okay, standard online gradient methods, we use natural gradient methods on the manifold because we want to respect the geometry of that. So we have the natural gradient descent with the Riemannian metric. But we also can do, people have been doing the mirror descent, which is using the Bregman divergence as a proximity function and then trying to find the extreme points and then maximize the following thing. Okay? So it turns out it was shown in this paper that the natural gradient descent of the primal coordinates is equivalent to mirror descent of the dual coordinates of the manifold. Okay, so these two algorithms are one and the same thing. Now there are two sets of coordinates on the same manifold. So we're dealing with the same manifold, but just two different coordinates in describing things. So they're not like going on two different manifolds, they're the same manifold. So this is the so-called Hessian manifold. The Hessian manifold has this property that the metric, the G, the Fisher information, is equal the Hessian of a convex function. It's very special. So general, this is the Fisher information. If it turns out to equal the second derivative of a convex function, that's the Hessian metric. Okay? So this happens when each of the following, or when any of the following condition holds. Namely, when G is equal Hessian, is if and only if this M, this underlying M manifold, admits a pair of bi-orthogonal coordinates, X and U, or there is a pair of affine coordinates with respect to a flat connections. There are two flat connections which are dual with respect to the G. Then they are the Hessian manifold. And the Hessian manifold describes this exponential model very well. Okay, so yeah, here is the slide that I promised I gave you about how statistical manifold can be always generated by the so-called contrast function. For any general divergence or contrast function, you can perform. So the second derivative gets you to the Riemannian metric, and the third derivative gives rise to the pair of affine connections. So here's xi and yj, divergence x and y, and then let y equal x. It turns out to be the same as yi xj. It needs some proof, it's not automatic, it needs to be proved. And this is, you take two xi xj and yk, and here's yi yj xk. So, but it turns out they give you a pair of third order quantity which can be properly identified as being affine connection, and furthermore, they are dual with respect to G in the precise sense that we just discussed earlier. Okay. So statistical structure very readily developed. Okay, so look like okay, on statistical manifold there is a dually flat. This Hessian manifold is a dually flat structure. So okay, so I very early on I did some calculations and proposed this so-called d alpha divergence function based on any convex function that would lead to this Hessian geometry. So I think I'm going to skip some part of it and just go. So this is the exponential model that leads to the Hessian. So this part is well known. Okay, this is the introduction to statistical manifold. This is absolutely the starting point. Okay. Now, where do we go from here? So we want to relax the Hessian model. We want to relax the applicability of the Euclidean geometry to a more general set, okay, not only the exponential family. So recently we are able to achieve that by proposing or by understanding what you call a partially flat case instead of dually flat. Dually flat, you have the two connections are both flat connections. Partially flat is you have a flat connection, and then another one is not, it's curvature free, but you have torsion. And this describes a very general case of statistical model. Namely, if you get any statistical model, okay, any parametric statistical model, I can use the original parameter as being the affine coordinates for some flat connection. I take the conjugate with respect to the G, to the Fisher metric, and then I'll get a partial flat model. So partial flat model is a very general way of constructing this geometry. So I think I've got yet to really skip some of the technical things on how do we go from a bi-orthogonal coordinates to so-called bi-orthogonal frame. So the first step is to show the bi-orthogonal coordinates, which only works for the Hessian geometry. We can enlarge it, we can generalize that to a bi-orthogonal frame. A frame, it doesn't have to be a coordinate frame. So the bi-orthogonal frame, so for any frame is a collection of vectors that span the whole tangent space. So for any of the frame, we can construct a connection which is curvature free, but which may carry torsion. So we show that for any frame, we construct an adapted connection which is curvature free and with torsion. If we take the G conjugate of that, which is this will equal the G bi-orthogonal frame. So with any G, we have G bi-orthogonal frame, and then we construct the connection. So these two notions, bi-orthogonal frame and bi-orthogonal, and then G conjugate connection, they are compatible. So with that, we are able to show a partially flat model. This is a partially flat geometry. The partially flat geometry essentially gives rise to the fact that the non-coordinate frame that we derive is nothing but just the gradient flow. The natural gradient flow. The natural gradient flow, which being commonly used in machine learning, why it's so powerful, it is actually just the conjugate connection with respect to the coordinates that you have. So we prove some the results of that. And then, so the condition, yeah, so we give a canonical partially flat, so-called pre-contrast or pre-divergence function. Okay? So from this function, we can induce a kind of a geometry. And we hope this function will be useful for machine learning because it generalizes the divergence function. So look like I really have to speak it through. Look like I'm short in time. So we also have extending this compatible with Kähler and compressify the geometry. So here, J squared is minus identity. This is almost complex structure. K squared is identity. This is a or split complex structure. And then they satisfy this compatibility condition. So these are definitions. So now, given these definitions, okay, and then we also revisited the so-called the L dual or L conjugate of a connection. The L conjugate of a connection, and then we also discussed the so-called omega conjugate of a connection. So we have a G conjugate, the L conjugate, and omega conjugate. So now we prove this theorem, which says for giving any connection, now we have a metric, we have a symplectic, omega homosymplectic form, and then we also have J, the complex, almost complex structure. Each of these can induce a transformation of this, and then but these three conjugations are linked in the sense that there are these four: the identity transform, the G conjugate, the omega conjugate, the L conjugate. They form a four-element Klein group. That's to say, if I repeat this G conjugate twice, omega conjugate twice, J conjugate twice, it becomes the omega, right? So this is a conjugation. Now, any combination of the two becomes the third. So if you have omega conjugate and then L conjugate, then becomes the G conjugate and so forth. And they are commutable. So these two are commutative algebra. So this is a very general statement, regardless of the properties of nabla, whether it has torsion, whether it has the connection with the quasi-coupling or so forth. So we have shown this. Now, in that, we can now enhance the statistical structure to a Kähler or para-Kähler structure. So given the statistical structure, we can now, so long as there is a J, so we need to find L. We need to find L. And if the following conditions, two of the following conditions hold, then the third one is hold, then it gives rise to what is called what we call para-Kähler manifold, Kähler or para-Kähler manifold. So, and so let's do this one, and then still more recently we are looking at how torsion can come into play. How torsion. Turns out that torsion plays a very important role, an interesting role. So turns out that, so this is a paper we just will come out, we just accepted in results in mathematics. So if we have a manifold and which with connections with torsion, we can define some coupling between the nabla and this L, this almost complex structure, so that when they are torsion coupled, when this condition is satisfied, then this L becomes integrable, this 9-Gauss tensor becomes 0, and the nabla becomes the para-holomorphic, or with respect to this L. Okay. So in this case, we get a Hermitian manifold, para-Hermitian manifold, which is a little bit weaker than the Kähler or para-Kähler manifold. What we showed is that if for this quadruple of connections, if any one is coulombic coupled with G, and any one is torsion coupled with L, then all four of them would be coulombic coupled with G, and all four of them are torsion coupled with L. And so all these connections come in